welcome to BKW Physics. I'm Mr. McConley. And before the video started, we started listing as a class what a scalar was and what a vector is. So scalars are based completely on magnitude. A number like 8 newtons, 8 meters, 8 kilometers per hour. Those are scalars because they represent a number that has magnitude, size, with a direction. Now if we move to the vector realm, now we take that same number, but we add a direction to it. So 8 newtons southeast, or 8 kilometers per hour at an angle of 15 degrees. Now we're talking about vectors. And then we decided to make a quick list of a few really common scalars and their corresponding vector. So speed is a very common scalar, and its corresponding vector, which direction matters, is velocity. Distance is displacement, mass is weight. So those are some really common scalar vector comparisons, and we're going to spend our time today talking about the vectors. So let me get rid of what's on the board here, and we're just going to focus in on just vectors right now. And basically what a vector is it's an arrow that represents the magnitude and the direction at the same time in a visual, graphical sort of way. So this vector right here says that there is some sort of magnitude pointing in that direction. This is called the tip, and this is called the tail, because this should look somewhat like an arrow with bow and arrow to you. And if I just drew another vector below it, and I drew it that size, you would say to yourself, that vector to me looks like it's about half as long as the one above it. Therefore, what's the magnitude of it? Half as big. Okay, that's the way vectors work. So, and both of these are actually pointing in different directions. So, that's kind of the basics of what a vector is. Now, what can you do with them? Well, the first things we can do with a vector is we can add vectors. So, addition. And when you add vectors, you could have an example possibly like this. Let's say a car drives 300 meters east, it stops, and then it drives 400 meters east. So what would that look like? So I'm going to use my meter stick here, and I'm going to say so you can do it corresponding with a ruler, every 10 centimeters will represent 1 centimeter on your ruler. So I said it drove, in this case I'll draw it 30 centimeters long, or you draw it as 3 centimeters, and I'll say that that represents 300 meters east. And then I stop. That means stop drawing the vector, put an arrowhead on it. Then it said the car continues for another 400 meters east. So what I have is I have two vectors that are added tip to tail, tip to tail. Okay? The tip of the first one goes to the tail of the second one, and so forth. Well, then the next question, usually in physics, is what is the result of this scenario? Now the result is from where you started to where you ended. So what would you say the result of these two vectors being added together is? Quite simply, 700 meters to the east. Okay? And I might draw it as one continuous vector, and I call it the resultant. I didn't say just result, I said resultant. Resultant. And it would be 700 meters east. And then actually that word resultant can be abbreviated with a capital R that has like a little line over it with a check mark almost. You see the way I did that? Flat line with a check mark, 700 meters east. So that's the way I could label that particular resultant. All right, moving on to another example, because that's pretty simple. What if this time the car drives 300 meters east, stops, turns around and drives 400 meters west? Okay, so this is another example here. We go 300 meters east. We stop. means draw the arrowhead on the end. Now, we have to start from that point and come back. Notice my arrows are overlapping one another. 400 meters west. What is my resultant arrow going to look like? Well, what does my resultant arrow always start at? It starts at where you started. And where does my resultant arrow always end at? It ends where you ended. So if I started here, this is my starting point, right there. Where did I end? Right there. Where is my resultant vector going to be, and how big is it going to be? It's actually going to be this big. And which way is it pointing?
West.
West, which makes sense, okay, because the bigger arrow was the west arrow. And how long will it be, this resultant? Everyone?
100 meters.
Yeah, it's going to be 100 meters, and it's going to be pointed in the westward direction. So in this case, there's my resultant. All right, moving on again to another type of problem. What if, now, let's change the scenario. Instead of a car, let's walk 40 meters east. So we're going to walk 40 meters east, and then we're going to stop for a moment, and then we're going to walk 20 meters north. Okay, what might that look like? Well, all right, if I say I'm going to go 40 meters east, let's say that's that long. All right, there is my 40 meters east. I stop, and now I'm going to go north. So in comparison to east, north must be upward, right? So we're going to be heading in this direction, and that's going to be about that long. So here is my 20 meters north. Okay, and I can put the little 90-degree symbol there to represent that that's a perfect 90. If you were drawing it and you had to draw it accurately, you would use a protractor to make sure that was an accurate measurement. Well, fine. Where's my resultant? My resultant is from where I? Patricia?
Start.
To?
Where you end.
Good. And on this picture, since there's no overlapping arrows, it's probably easiest to draw the resultant right in place. And my resultant will be labeled as how big. Now at this point, you got a choice. You could actually use mathematics to calculate it out, right? Because you know a squared plus b squared equals c squared. You could do that. But since you drew it to scale and you drew it accurately, you could also take and measure this out. And mine measures about 48, which means it would be 48 meters. And what direction would you call that? Northeast. Okay. Now, if I was specifically asking for an angle, like I really wanted to know what angle this was right here, how would you do that? So this is one method. This is measure it out, actually scale it out, measure it, and label it that way. The other way, method 2, which I was referring to, you could use a squared plus b squared equals c squared, get an exact answer. And then for the angle, you could do opposite over adjacent, which is tangent. Okay, so you could apply some mathematic principles and actually get the exact angle and the exact length that way. Does that make sense? Well, there's one more scenario that gets a little bit more messy, we'll say. In this scenario is, what if the things don't meet at very convenient angles? Like, let's say one person is pulling 50 newtons at 0 degrees, and another person is pulling 40 newtons at 30 degrees. Well, what might that look like? All right, well, the 50 newtons at 0 degrees, let's say 0 degrees is that way. So the 50 newtons at 0 degrees would simply looks something like this. Here's my 50 newtons at 0 degrees. But then where do I connect my 40 newtons at 30 degrees? What have we done in every other picture? We started with the first arrow and we connected the second arrow to the tip of the first arrow. We still have to continue that same process. So now the 40 newton one has to start where the first one ended. Well, I'm going to extend this out a little bit. I would pull out a protractor here, and you would pull out one also, and you would measure 30 degrees, boom, put a little tick for yourself, and then I would say, okay, from that point, I'm going 40 newtons at 30 degrees. All right, you following that? See how we created that? And if you're following along and don't have a protractor, that's all right. Just kind of for this moment, just kind of get it close. Well, where is my resultant? My resultant is always from where I started to where I ended up. And so I'm going to connect those two. That's labeled as my resultant. And how do I figure out how big this resultant is? Because now I got a problem. This is not a right triangle, and when you don't have a right triangle, you can't do a squared plus b squared equals c squared, and you can't do tangent because those things only work with right triangles. I don't have a right triangle. What do I do? Well, at this point, that's why you should have drawn it to scale and accurately, because we can actually take and measure this. Mine happens to measure about 87. And I can say it's 87 newtons. And I can also pull out my handy-dandy protractor again, here it is, and measure the angle. And mine measures to be about a 24-degree angle. So I can say the resultant is 87 newtons at 24 degrees. Now, one more thing I want to do is I want to show you that vectors can be added in many different orders. Let me explain. If I take vector A, and we'll just draw it straight up. It's not real important you get any specific lengths on these, just try to be consistent. If I say A is pointing that way, and then B is going to point this way, and it's added, of course, to the end of A, tip to tail, same method. And then I'm going to say C is kind of pointed this way, and it's that long. Then where's my resultant? Well, my resultant's from where I started to where I ended up. Just the same method we've been doing. But what if I switched the order of these? So what if I said, okay, let's start with B. Now notice, I'm going to keep B the same length, and for mine, mine's about a 24. So I'm going to keep B the same length. And I'm also going to keep it pointing in the same direction. See how this direction is the same as that? And then I'm a little off. But you see how those are kind of pointing in the same direction? I've kept the direction the same and the length the same. So this is B. Now what if instead of tacking C on the end, what if I tack A on the end right now? So which way does A go? Well, A goes straight up, like that. And I'm trying to keep A the same length, and notice I'm pointing them both up in the same direction. So now I've tacked A onto the end. Now finally, the one I have ignored is C. Now C is shorter, and I'm going to put that on the end of A. So A, B, and C are all the same length in both pictures and pointing the same direction individually in each picture. And what does my resultant end up? From where I started to where I ended. And what do you notice visually? I know you can take out your ruler and start measuring. Yeah. But what do you notice visually about these two resultants? They're the same length and same direction, same angle, pointing the same degree. So it does not matter which order you add vectors, you'll always get the same result in. And for today, Kyra, that's physics.